Have you ever wondered how far humanity could go in its pursuit of knowledge? Could we, as a civilization, ever overcome the ultimate boundaries of existence? What happens when even the most advanced technology fails to answer the fundamental questions of reality? These are the mysteries that have haunted thinkers for centuries and continue to challenge us today. Imagine a civilization so advanced that it spans galaxies, with technologies capable of capturing every wavelength of light from the farthest corners of the observable universe. A civilization that has unlocked the secrets of the quantum realm, colonized countless star systems, and reshaped entire galaxies to suit its needs. And yet, despite their unimaginable power, they find themselves unable to answer one of the most profound questions. Are they truly alone in the cosmos? This is the story of the great arcships, colossal vessels that carry the dreams and ambitions of a civilization reaching for the stars. But as their journey unfolds, they realize that the universe they inhabit is just one of infinitely many. What does it mean to confront infinity? Can any civilization, no matter how advanced, grasp the scale of an infinite multiverse? And if they can't, what is the ultimate limit of knowledge? These questions set the stage for an extraordinary tale of exploration, despair, and discovery. A story of how a civilization, in its relentless pursuit of answers, discovers not only the vastness of the cosmos, but also the boundaries of their own understanding. So how far could we go? How much could we ever truly know? The infinite multiverse. It began as a whisper among their greatest minds, an idea so radical that many dismissed it outright. For eons, the civilization had looked upon their universe as the ultimate arena of existence. Vast, incomprehensibly large, yet singular. They had built galaxy-spanning observatories, devices so sensitive they could detect even the faintest remnants of light from the birth of their cosmos. They had peered into the quantum realm, uncovering particles and forces that danced on the edge of reality. Their arcships had traveled across intergalactic voids, bridging the unimaginable distances between galaxies. Yet, despite these monumental achievements, something remained elusive. The realization came not from one breakthrough, but from a convergence of discoveries across disciplines. Slowly, piece by piece, the evidence pointed to a staggering conclusion. Their universe was not alone. It was but one in a vast multiverse, an infinite collection of universes, each with its own set of physical laws, its own histories, and its own possibilities. At first, the idea was exhilarating. The multiverse promised a playground of infinite variety. If one universe could give rise to life and intelligence, how many more might teem with civilizations beyond their imagination? If their own cosmos held wonders and mysteries, what untold marvels might lie in the realms beyond? It seemed as though the multiverse was the ultimate frontier, a boundless expanse of exploration and discovery. But as they delved deeper into the implications, the exhilaration gave way to unease, and unease to despair. The multiverse was not just infinite in its scope, it was infinite in every possible way. For every universe that mirrored their own, there were countless more, where the laws of physics rendered stars impossible, or where time flowed in directions incomprehensible to their minds. For every universe that harbored intelligent life, there were infinite others that were empty and barren. This infinity posed a paradox. In a finite universe, questions like, "Are we alone?" could theoretically be answered with enough exploration and data. But in an infinite multiverse, such questions became meaningless. Any finite amount of information they could gather was dwarfed by the endless unknown. Were they a common occurrence or a rare anomaly? Did life like theirs make up 1% of all universes, or 99%? The numbers lost all significance in the face of infinity. Their calculations always returned the same result: 0. Not because they lacked knowledge, but because no amount of knowledge could ever make a dent in the infinite. The multiverse rendered probabilities irrelevant. For every possibility they could imagine, there existed infinite universes where it was true, and infinite universes where it wasn't. This realization was not just an intellectual challenge, it was an existential one. It forced them to confront the limits of their understanding. Their entire civilization, the most advanced in the history of their cosmos, was reduced to a single, insignificant data point in an ocean of infinity. The multiverse was a mirror reflecting not their achievements, but their insignificance. And so, they were left with an impossible question. How do you measure yourself against the infinite? How do you find meaning in a sea where every discovery is drowned by countless unknowns? The multiverse was no longer a frontier to conquer. It was a reminder of their ultimate limitations, a vast, uncaring expanse that would forever lie beyond their grasp. The civilizational journey. In the beginning, the civilization's journey was like many others, a story of curiosity and survival. They were once beings confined to their homeworld, gazing at the stars with wonder. The celestial patterns above them inspired awe and questions. What were those points of light? Were they gods, guiding their fate, or were they destinations waiting to be reached? Slowly, over centuries, their curiosity evolved into something more structured, an organized effort to understand the world around them. They developed tools and methods, and from those humble beginnings, their path to greatness was set. At first, their discoveries were simple, yet transformative. They learned to harness fire, to farm, and to build shelters. These advancements allowed them to escape the precariousness of survival and turn their focus outward. They began to study the heavens, charting the movements of the stars, the cycles of the moon, and the rhythms of the seasons. Over generations, this knowledge became the foundation of their civilizations, influencing their myths, religions, and early sciences. As their understanding grew, so too did their ambitions. They invented devices to extend their senses, telescopes to peer into the cosmos, and microscopes to uncover the hidden details of their world. The scientific method emerged, giving them a way to systematically explore the unknown. Questions that had once seemed insurmountable were now within their reach, and the pace of discovery quickened. Over centuries, they unlocked the secrets of gravity, energy, and matter, piecing together the laws that govern the universe. The next great leap came when they turned their gaze from the sky to their own world, realizing they could harness its energy. They built machines powered by steam, then electricity, and eventually nuclear fusion. These advancements propelled them into the industrial age, where their mastery over energy and materials transformed their societies. They became a Kardashev Type 1 civilization, fully harnessing the power of their planet. But they did not stop there. With the resources of their world secured, they turned their attention outward to the vast expanse of space. They constructed rockets and launched probes, sending them to explore their neighboring planets. They established colonies on moons and distant worlds, transforming barren landscapes into habitable environments. Their solar system became a sprawling network of outposts, research stations, and industrial hubs. The move from a planetary civilization to a star-faring one marked a turning point in their history. They began to dream of the stars, not as distant lights, but as destinations. They developed technologies to harness the energy of their sun, constructing Dyson swarms, vast arrays of solar collectors that captured its immense power. With this energy, they built arc ships, colossal vessels capable of carrying entire populations across interstellar distances. These arc ships were not just tools of exploration. They were self-sustaining ecosystems, capable of surviving journeys lasting thousands or even millions of years. Inside, their passengers lived, worked, and thrived, carrying the hopes of their civilization to distant star systems. Some of these voyages succeeded, establishing new colonies in other parts of the galaxy. Others were lost to the void, their fates unknown. But the civilization pressed on, undeterred by the risks. As they expanded into the stars, their understanding of the universe deepened. They built particle colliders that spanned entire solar systems, smashing matter together at unimaginable energies to uncover the building blocks of reality. They constructed telescopes so powerful that they could peer billions of years into the past, observing the birth of galaxies and the first moments of the cosmos. They developed quantum computers capable of simulating entire star systems, predicting their behavior with stunning accuracy. Yet, as their knowledge grew, so too did their realization of the universe's complexity. The more they learned, the more they understood how little they truly knew. Mysteries like dark matter, dark energy, and the unification of quantum mechanics and gravity remained unsolved. These barriers loomed like unscalable mountains, challenging their belief that all questions could eventually be answered. Despite these obstacles, they continued to push the boundaries of what was possible. They reached the level of a Kardashev Type II civilization, harnessing the energy of entire stars. They transformed entire solar systems into interconnected hubs of activity, using their immense resources to fuel their insatiable quest for knowledge. Black holes became their power sources, their immense gravitational energy driving experiments that probed the very fabric of space-time. However, the limits of their understanding became increasingly apparent. They discovered that some questions might never be answerable, not because they lacked the tools or the will, but because the nature of reality itself imposed barriers. The universe, they realized, was not infinite in its accessibility. There were regions of space-time they could never reach, events they could never witness, and questions they could never fully resolve. The greatest challenge came when they began to theorize about the multiverse. This idea, born from their exploration of quantum mechanics and cosmology, suggested that their universe was just one of infinitely many. Each universe in this multiverse had its own unique set of physical laws, its own history, and its own possibilities. The implications of this discovery were staggering. If the multiverse were real, it rendered many of their questions meaningless. How could they measure their place in the cosmos when the cosmos itself was infinite? How could they calculate probabilities or understand their uniqueness when every possibility existed somewhere? This realization cast a shadow over their achievements. They had explored the stars, reshaped galaxies, and unlocked many of the universe's secrets, yet they found themselves dwarfed by the enormity of the multiverse. Their entire civilization, the most advanced in the history of their universe, was reduced to a single data point in an infinite sea. No matter how far they went, no matter how much they discovered, there would always be questions they could never answer. For all the barriers they faced, they refused to give up on their quest for understanding. They believed that the pursuit of knowledge, even in the face of infinity, was itself a form of meaning. Their story was not just about the answers they found, but about the relentless drive to explore, to question, and to grow. In this, they found purpose. Their journey was far from over, and as they stared into the infinite expanse of the multiverse, they carried with them the hope that somewhere, somehow, they might discover not only the secrets of the cosmos, but also the ultimate truth about themselves. Biological and technological limitations. For all their monumental achievements, the civilization was haunted by an undeniable truth. Their very essence was shaped by their biological origins. Their intelligence, creativity, and capacity for curiosity, while extraordinary, were limited by the finite structure of their minds and bodies. Their brains, evolved for survival on a single planet, were astonishingly complex but fundamentally constrained. They could process only so much information at a time, and their perceptions were narrow, limited to a small slice of reality defined by their senses. Memory was imperfect, prone to fading or distortion over time. Their physical bodies were fragile, requiring food, water, rest, and protection from the harshness of the universe. Even their lifespans, though extended by technological advancements, were mere moments on the cosmic timescale. How could beings with such constraints hope to grasp the infinite mysteries of the cosmos? To push beyond these limitations, they turned to technology. At first, they sought to augment their biology. Cybernetic enhancements improved their physical resilience, extended their lifespans, and expanded their cognitive capacities. Neural interfaces allowed them to connect directly to computational networks, accessing vast reservoirs of knowledge in real time. For many, the line between the organic and the synthetic began to blur. As their ambitions grew, they took the next step, escaping the confines of biology entirely. Entire generations transitioned into digital consciousness, uploading their minds into immense computational systems. In these virtual domains, thought was no longer bound by the constraints of neurons and synapses. They could process information at unimaginable speeds, simulate entire worlds, and explore concepts that their biological counterparts could scarcely comprehend. Yet even in this new form, they encountered barriers. Their original biological frameworks, the product of millions of years of evolution, continued to shape their perceptions and thought processes. No matter how advanced their systems became, they were still rooted in the biases and limitations of their creators. Artificial intelligences, designed to think beyond human constraints, often mirrored the priorities and blind spots of those who built them. Though faster, more efficient, and more powerful, these machines were not as free from limitation as they had hoped. Their technological triumphs brought them closer to the cosmos's most elusive mysteries, but also exposed new challenges. In their exploration of the quantum realm, they encountered the Heisenberg uncertainty principle, which limited their ability to precisely measure fundamental particles. They discovered that no matter how advanced their tools became, there were aspects of the universe that could not be fully known. The deeper they delved into the subatomic world, the more it seemed to resist their efforts to map it completely. On a cosmic scale, the limitations were equally daunting. The vastness of space and the finite speed of light meant that many regions of the universe were forever beyond their reach. Even as they colonized galaxies and harnessed the energy of entire star systems, they were bound by the unyielding laws of nature. They could see the universe's grand design, but only from a narrow vantage point defined by their own perspective. Despite these challenges, they refused to accept their limits as final. They developed artificial intelligences with radically different architectures, hoping to create systems that could think in ways fundamentally alien to their own. These intelligences were not meant to replace them, but to complement their understanding, providing insights into aspects of the universe their own minds could not grasp. Yet even these new systems, for all their brilliance, seemed to reflect the boundaries of the civilization that created them. The civilization also experimented with genetic engineering, modifying their biology to enhance their cognitive and physical abilities. They created entirely new forms of life, tailored to survive in extreme environments and think in ways no organic mind ever could. These creations, while extraordinary, were still extensions of the same fundamental desire, to overcome the barriers that separated them from the ultimate truths of existence. As they pressed onward, their quest became as much about understanding themselves as it was about understanding the universe. They sought not only to push the boundaries of their knowledge, but to redefine what it meant to be alive, to think, and to explore. Each breakthrough brought new possibilities, but also new questions about the nature of intelligence, consciousness, and the limits of knowledge itself. Their journey through the cosmos had shown them that no matter how powerful their technology became, they would always be bound by some form of limitation, whether biological, technological, or imposed by the universe itself. Yet it was this very struggle that defined their identity. They were a civilization driven by the relentless pursuit of understanding, determined to push past every barrier, no matter how insurmountable it seemed. And so they pressed on, their efforts fueled by the hope that somewhere beyond the horizon they might find the answers they sought, or perhaps something even greater. Interstellar and intergalactic expansion. Faced with the limitations of biology, technology, and the boundaries of the known universe, the civilization turned its attention to the stars. They understood that to overcome these constraints, they needed to expand their reach far beyond their home systems. Their gaze shifted from the confines of their galaxy to the endless expanse of interstellar and intergalactic space. This was not just a journey of survival, but a mission to unlock the secrets of existence itself. The civilization's interstellar efforts began with their arc ships, massive vessels designed to carry entire populations across the gulfs of space. These were no ordinary spacecraft. They were self-sustaining ecosystems capable of enduring journeys that spanned millennia. Inside, passengers lived in suspended animation, their biological needs reduced to the bare minimum, while advanced artificial intelligences piloted the ships through the cosmic void. These journeys were not without risks. Many ships vanished, swallowed by the darkness between the stars, their fate unknown. Yet for every ship lost, others succeeded, planting colonies in distant systems and extending the reach of their civilization. Over time, their methods of travel evolved. They built immense light sails, propelled by powerful beams of energy from home systems, allowing smaller, faster crafts to leap across vast distances. They developed wormhole technologies, creating shortcuts through space-time itself, though these remained experimental and fraught with dangers. For the most distant targets, they relied on generational ships, massive habitats where entire societies lived, worked, and died during the long journey to a new star. Their intergalactic expansion posed even greater challenges. While they had mastered the energy of entire stars, moving between galaxies required energy on an almost incomprehensible scale. To overcome this, they constructed Dyson swarms around dying stars, capturing every last watt of energy to fuel their intergalactic voyages. They also learned to harness the rotational energy of black holes, extracting power from the very fabric of space-time. With these advancements, they launched expeditions to neighboring galaxies, reaching the edges of the known universe. Communication between these far-flung colonies became an insurmountable obstacle. The vast distances introduced delays measured in centuries or millennia, making real-time coordination impossible. Each colony became its own autonomous entity, adapting to the unique challenges of its environment. Despite this, they remained united by a shared purpose: the pursuit of knowledge. Information from every corner of their civilization was collected, analyzed, and shared, creating a tapestry of understanding that spanned the stars. As they ventured deeper into the cosmos, they encountered not only physical challenges, but philosophical ones. What did it mean to expand endlessly into the void? Were they driven by a genuine desire to explore, or were they fleeing the realization of their own limitations? The infinite multiverse loomed over their efforts, reminding them no matter how far they traveled, they could only ever explore a finite portion of infinity. Their expansion also brought them closer to the mysteries they sought to solve. They observed the structures of the cosmos on an unprecedented scale, uncovering patterns in the distribution of galaxies and dark matter that hinted at deeper laws of nature. They built observatories that could detect the faint whispers of gravitational waves from the earliest moments of the universe, capturing echoes of creation itself. Each discovery brought them closer to understanding the nature of reality, but also revealed how much they still didn't know. As their civilization stretched across galaxies, they began to sense the looming shadow of the ultimate limits. They had conquered vast distances, harnessed incredible energies, and built a network that spanned the stars, but they were still bound by the fundamental laws of physics. The speed of light, the decay of information over time, and the relentless march of entropy placed boundaries on their reach. The expansion set the stage for a profound reckoning. They had reached the threshold of their capabilities, standing on the precipice of the unknown. Beyond lay the cosmic limits, the unobservable regions of the universe, the mysteries of black holes, and the boundaries imposed by quantum mechanics. These would define their next great challenge and lead them into the most difficult questions of all. What lies beyond what can be known? And how far could even the most advanced civilization go before it must confront the boundaries of the universe itself? Cosmic limits. As the civilization pushed the boundaries of its interstellar and intergalactic expansion, it became increasingly clear that the universe itself imposed fundamental limits. For all their ingenuity and technological prowess, there were barriers they could not cross, horizons they could not reach, and mysteries that resisted every effort to unravel. These cosmic limits, embedded in the fabric of reality, defined the ultimate challenges of their existence. One of the first and most immutable boundaries they encountered was the speed of light. This universal constant dictated not only the pace of their interstellar voyages, but also the limits of their communication and observation. No matter how advanced their propulsion systems became, the distances between galaxies meant that travel was measured in millennia, even for their fastest ships. The information sent from one end of their empire to another was hopelessly delayed, making real-time coordination across vast cosmic distances impossible. Light, traveling at its constant speed, could only traverse so far in the 13.8 billion years since the universe's birth. This created a cosmic horizon, the observable universe, that defined the furthest reaches of what they could ever see or measure. Beyond this horizon lay regions of space and time forever inaccessible to them, not because they lacked the technology, but because the universe itself had not yet allowed its light to reach them. Even within the observable universe, they faced another immutable limit: the expansion of the cosmos. The discovery of dark energy revealed that the universe was not just expanding, but accelerating in its growth. Over time, galaxies at the edge of the observable universe would recede faster than the speed of light, slipping beyond their view and taking with them any chance of interaction or observation. The universe, for all its vastness, was becoming increasingly isolated, fragmenting into unreachable islands of matter. Their efforts to probe the quantum realm brought them face to face with another barrier: the Heisenberg uncertainty principle. This fundamental feature of quantum mechanics made it impossible to simultaneously measure certain pairs of properties, like the position and momentum of a particle, with absolute precision. No matter how advanced their instruments became, they could never escape this inherent fuzziness at the smallest scales. The quantum realm remained a domain of probabilities and uncertainties, defying their desire for absolute knowledge. Black holes presented perhaps the most tantalizing and frustrating of cosmic limits. These objects, formed from the collapse of massive stars or the merger of galaxies, were perfect keepers of secrets. Their event horizons marked a one-way boundary. Once crossed, nothing, not even light, could escape. Everything that fell into a black hole became hidden from the universe outside, leaving only its mass, spin, and charge as observable properties. The information about what the black hole had consumed seemed to vanish, leading to one of the great paradoxes of modern physics, the black hole information paradox. For the civilization, black holes were both a source of fascination and despair. They built observatories to study these enigmatic objects, seeking clues about the nature of space-time and gravity. They even attempted to approach the event horizon, sending probes to gather data from the brink of the unknown. But the closer they came, the more they realized that the answers they sought were locked away, perhaps forever. The singularity at the heart of a black hole, where all known laws of physics broke down, represented a boundary they could neither cross nor fully understand. Another limit loomed even larger: entropy. The second law of thermodynamics dictated that the universe tended toward greater disorder, a relentless march toward a state of maximum entropy. Over unimaginable timescales, stars would burn out, galaxies would dissolve, and black holes would evaporate. The universe, once vibrant and full of structure, would fade into a cold, dark expanse, a state known as heat death. This ultimate fate imposed a temporal boundary on their existence, forcing them to confront the reality that even their most advanced technologies and civilizations were impermanent. Despite these barriers, the civilization did not surrender to despair. They saw each limit not as an end, but as a challenge to be understood and navigated. They probed the edges of the observable universe, seeking patterns in the distribution of galaxies that might hint at what lay beyond. They developed theories to explain the nature of dark energy and attempted to find ways to manipulate it, hoping to slow or reverse the universe's accelerating expansion. Their experiments in quantum mechanics grew increasingly ambitious. They explored the phenomenon of quantum entanglement, where particles separated by vast distances could remain mysteriously connected, sharing information instantaneously. While they could not break the speed of light barrier for physical travel or communication, they hoped to exploit entanglement to achieve faster-than-light transmission of information. Though the results were promising, the fundamental nature of quantum mechanics remained elusive. Faced with the mysteries of black holes, they turned to the idea of holography, a theory suggesting that all the information within a region of space could be encoded on its boundary. This concept, though abstract, offered a tantalizing possibility that the secrets hidden within black holes might be recoverable, encoded in the subtle patterns of their event horizons. The civilization built vast arrays of detectors, hoping to decode these patterns and peer into the heart of the black hole's mystery. Yet, as they pursued these frontiers, they began to sense that some questions might never have answers. The universe, for all its grandeur, seemed designed to withhold its deepest truths. Beyond the observable cosmos, beyond the event horizons of black holes, and beyond the uncertainties of quantum mechanics, lay a realm of permanent unknowability. It was not just a matter of insufficient technology or understanding. It was a reflection of the inherent structure of reality. The realization that the universe imposed fundamental limits did not deter them. Instead, it inspired a new phase of their journey. If they could not uncover all the secrets of the cosmos, they would strive to understand why those limits existed. This quest brought them to the brink of their next great mystery, the multiverse. If their universe was just one of many, perhaps the answers to their questions lay not within, but beyond, the ultimate challenge and the subject of their next pursuit. The multiverse conundrum. The civilization's relentless pursuit of knowledge brought them to a breathtaking yet disorienting revelation. Their universe, vast and intricate as it was, might be just one of infinitely many. The concept of the multiverse, born from theoretical physics and mathematical models, suggested that what they had long considered the entirety of existence was merely a bubble in a sea of countless others. Each of these universes could have its own set of physical laws, dimensions, and possibilities, forming an infinite landscape that defied comprehension. At first, the idea of the multiverse seemed like an expansion of their cosmic horizon, a new frontier promising endless discoveries. If their universe held wonders like galaxies, black holes, and intelligent life, what marvels might the multiverse contain? The possibilities seemed boundless, universes with dimensions beyond imagining, where time flowed in reverse or not at all. Universes where the constants of physics allowed for forms of life and matter utterly alien to their understanding. But as they began to grapple with the implications of infinity, the exhilaration gave way to profound challenges. The multiverse was not just infinite in scope, but infinite in every conceivable way. For every universe like theirs, there were infinite others where the laws of physics rendered stars impossible, or where life never emerged. For every intelligent civilization, there were infinite empty universes, vast voids of potential never realized. The sheer scale of the multiverse introduced a fundamental problem: measurement. In their universe, they could explore, observe, and calculate probabilities. But in an infinite multiverse, these concepts broke down. If there were an infinite number of universes with intelligent life, how could they measure the rarity or commonality of their own existence? Any finite data they gathered from their universe, or even from neighboring ones, was rendered insignificant in the face of infinity. Every percentage they calculated, every ratio they derived, collapsed into irrelevance. This issue, known as the measure problem, struck at the core of their quest for knowledge. They sought to understand their place in existence, but the multiverse offered no definitive answers. Were they unique, a rare phenomenon in an otherwise barren multiverse? Or were they just one of countless civilizations, scattered across infinite realities? The multiverse held every possibility, but it also obscured every certainty. Their attempts to explore the multiverse were fraught with difficulties. They had developed theoretical models suggesting ways to access other universes, using quantum tunneling or manipulating the boundaries of space-time. These efforts, however, were limited by the constraints of their own physics. The gateways they opened were unstable, and the glimpses they caught of other realities were fleeting and incomplete. Each experiment raised more questions than it answered, deepening the mystery of the multiverse rather than resolving it. Even if they could traverse the multiverse, they faced a paradox. No matter how many universes they explored, there would always be infinitely more beyond their reach. The multiverse, infinite in its nature, presented a boundary they could never cross. Every discovery they made, every insight they gained, was dwarfed by the infinite expanse of what remained unknown. Their greatest achievements seemed small against the backdrop of endless possibility. Philosophically, the multiverse forced them to confront profound questions about meaning and purpose. If every possible version of themselves existed somewhere in the multiverse, what did their actions mean? Were they merely one iteration among countless others, their struggles and triumphs mirrored and contradicted across infinite realities? Or was there something unique about their particular universe, something that set it apart in a way they could never fully understand? Despite these challenges, they pressed on, driven by the same curiosity that had propelled them to the stars. The multiverse, for all its enigmas, was a frontier unlike any other. They sought to decode its rules, to understand the mechanisms by which universes emerged and evolved. They hoped that within the multiverse's infinite variety, they might find patterns or structures that could offer some measure of comprehension. Their work on the multiverse brought them to the edge of a profound realization. If their universe was not unique, then perhaps the answers they sought were not to be found within it. The multiverse was not just a collection of universes. It was a challenge to their very understanding of existence. The boundaries they had encountered in their universe, spatial horizons, quantum limits, entropy, might themselves be mere reflections of deeper multiversal truths. As they stood on the precipice of this understanding, the civilization faced its greatest question yet. If the multiverse truly represented the infinite, was it even possible to know anything meaningful about it? And if knowledge of the multiverse was forever out of reach, what did that mean for their quest for understanding? These questions, profound and unsettling, prepared them for the next step in their journey. If their own biology and technology had once limited them, and now even the multiverse posed insurmountable challenges, they would need to go beyond their current forms of existence. The next phase of their evolution would not merely involve better tools or faster ships, but a transformation of consciousness itself, a leap into a state of being that might finally allow them to comprehend the incomprehensible. The final horizon, infinity. As the civilization evolved into forms of consciousness that transcended biology, even their most advanced minds were drawn toward a singular, daunting concept, infinity. Infinity was no longer just a mathematical abstraction or a philosophical curiosity. It had become the ultimate horizon of their understanding, a boundary that seemed to defy comprehension itself. To grasp it, they would have to confront the very nature of existence, knowledge, and meaning. Infinity pervaded every aspect of their exploration. In the multiverse, it presented an unending landscape of possibilities, where every potential reality existed somewhere. In the quantum world, it manifested as the endless complexity of particle interactions, the infinite dimensions of Hilbert space, and the ceaseless oscillations of quantum fields. On the cosmic scale, infinity revealed itself in the ever-expanding universe, where galaxies receded faster than light, and the observable cosmos became a shrinking island in an immeasurable sea. Their attempts to quantify infinity only deepened its mystery. They had long mastered the mathematics of infinities, from the work of their ancient predecessors to the insights of modern computational models. They understood that not all infinities were equal. Some were larger or more complex than others. Yet, when applied to the multiverse or the quantum realm, these distinctions often collapsed into paradoxes. How could they weigh their place in an infinite multiverse when every possibility existed in uncountable repetitions? How could they calculate probabilities when infinity rendered every calculation both trivial and insurmountable? As they explored further, they began to see infinity not as a barrier to knowledge, but as an intrinsic property of existence. It was not something to be conquered or fully understood, but something to be engaged with, an eternal question that defied resolution. This realization reshaped their quest, turning it inward. If the infinite could not be fully grasped, could it still be experienced? Could they find meaning in exploring an endless reality, even if they could never reach its edges? To approach these questions, they pushed their understanding of consciousness to new heights. They developed forms of awareness that could operate within the framework of infinity, perceiving not discrete entities, but the relationships and patterns that emerged across infinite scales. These minds could process not just individual truths, but entire systems of truths, seeing the infinite as a coherent whole rather than an overwhelming chaos. Yet, even these enhanced forms of consciousness found themselves humbled by the vastness of their inquiry. For every insight gained, infinity revealed new layers of complexity, new dimensions to explore. This pursuit led to a profound philosophical shift. They began to ask whether the act of understanding was itself the goal. Was their drive to explore the cosmos a reflection of something deeper, a fundamental aspect of consciousness that sought connection with the infinite? If so, their journey was not about reaching an end, but about engaging in an eternal process, a dance with the infinite that could never be completed but would always hold value. As they contemplated these ideas, they turned their attention to the fabric of the multiverse itself. If each universe was a bubble in an infinite sea, what lay beyond the multiverse? Did infinity itself have a structure, a logic that transcended even the physical laws of individual universes? Could there be a meta-reality, a domain where infinities converged and the boundaries of existence dissolved into something more fundamental? To explore these questions, they embarked on their most ambitious experiment yet. They constructed a vast network of consciousness, spanning galaxies and dimensions, designed to merge their collective understanding into a unified perspective. This network, more than a tool, was an embodiment of their quest, a living representation of their desire to engage with the infinite. It allowed them to think not as individuals, or even as a civilization, but as an entity that could glimpse the multiverse from a perspective beyond time and space. Yet, as they prepared to activate this network, they knew they were approaching a final boundary. Beyond this point lay questions that might never be answered. What was the ultimate nature of reality? Was infinity itself an illusion, a construct of limited minds attempting to grasp the ungraspable? Or was it the ultimate truth, the source from which all existence flowed? These questions set the stage for their greatest challenge, confronting the infinite, not as a concept, but as a lived reality. The final horizon of their journey was not a destination, but a transformation, a leap into the unknown, where the boundaries of knowledge, existence, and meaning would dissolve into the infinite expanse. The stage was now set for the ultimate exploration, one that would transcend everything they had ever known. The limits of knowledge. The civilization had reached the threshold of the infinite, poised at the brink of understanding all that could be known, and yet humbled by the vastness of what lay beyond. Their journey had spanned eons, from their first cautious steps into the unknown to their transformation into entities capable of perceiving reality across infinite scales. They had conquered the barriers of biology, mastered the energy of galaxies, explored the depths of quantum mechanics, and ventured into the multiverse. Yet, despite all their achievements, they found themselves grappling with a profound realization. There are limits to knowledge, and these limits are not failures, but intrinsic features of existence. Their confrontation with infinity revealed that knowledge itself might be a process without an end. Each question answered opened new realms of inquiry. Each mystery unraveled revealed deeper layers of complexity. The multiverse, quantum mechanics, and the cosmic scale had taught them that some aspects of reality could never be fully grasped. Whether due to the fundamental laws of physics, the constraints of logic, or the sheer immensity of the infinite, there would always be horizons they could not cross. Yet these limits did not diminish their achievements. Instead, they gave their journey meaning. The civilization came to see the pursuit of knowledge not as a quest for ultimate answers, but as an expression of their existence, a celebration of curiosity, creativity, and the drive to explore. The very act of seeking, of striving to understand, was a form of connection to the universe, a way of participating in its unfolding story. As they stood on the precipice of infinity, they reflected on the journey that had brought them there. Their first questions, born from the simple act of looking at the stars, had grown into a civilization-wide endeavor that spanned galaxies and dimensions. They had built tools to extend their senses, created minds that transcended biology, and explored realms of reality that their ancestors could never have imagined. Each step had brought them closer to the universe, not as an object to be understood, but as a partner in a cosmic dialogue. The civilization realized that meaning was not something to be found at the end of their journey, hidden in the final answers to their questions. It was something they had created along the way. In their exploration, in their relentless curiosity, in their willingness to face the unknown, they had given their existence a purpose that transcended any single discovery. And so, they turned their gaze back toward the infinite, not with despair, but with hope. They knew that their journey was not over, that there would always be new horizons to explore, new mysteries to ponder, and new ways to connect with the universe. They embraced the idea that their role was not to conquer the infinite, but to participate in it, to weave their story into the fabric of existence, and to be part of the endless dance of understanding and being. The limits of knowledge were not walls to be broken, but horizons to be approached, always expanding, always inviting. And within those limits, the civilization found a profound truth. The search for meaning, for understanding, for connection, was itself the greatest journey of all. In the end, they realized that the infinite was not something to be solved or overcome. It was a mirror reflecting their own nature, a boundless source of inspiration that would guide them for eternity. And so, they continued, their journey stretching forward into the infinite, knowing that the questions would never end, and that was precisely why they mattered. If you look through a powerful telescope at any objects in the universe surrounding you and observe that they are all moving away from you, you might decide that you have a repelling force or that space itself is expanding. Another possibility is that you are at the center of a past explosion and everything is moving away from its center. At first glance, all of these and some other explanations might seem reasonable, but scientists always talk about the expanding universe as if other alternatives are not suitable. One of the most incredible facts associated with Einstein's theory of general relativity is that it relates space-time, matter, and energy. Matter and energy dictate how space-time should curve, and space-time tells matter how to move. If we learn how all matter and energy are distributed in the universe at a certain point in time and how they are moving, we can reconstruct the curvature of space-time and the evolution over the lifetime of the universe. Observing the galaxies in the universe, we see that the gravitational dynamics of neighboring galaxies have the most influence on the closest galaxies to us. For example, the Milky Way and Andromeda are moving towards each other. Other galaxies and local groups will eventually merge as well. The rest of the galaxies are attracted to the nearest masses, large galaxies, galactic groups, and clusters. In any relatively small region of space, ranging from a few million to tens of millions of light years in size, the mass of this space determines how galaxies will move. However, on larger scales, things don't work the same way. Small-scale movements, known as regular velocities, can reach a few thousand kilometers per second, but they are overshadowed by a stronger effect that can only be seen on larger scales. The farther a galaxy is from us, the faster it is moving away from us. This empirical observation is known as Hubble's law, which postulates that the observed recession velocity of galaxies is proportional to their distance from us. The constant of proportionality in this relationship is known as the Hubble constant. It has been measured quite accurately, and you can see its value on your screen right now. But why does this happen? In reality, why is everything moving away from each other? When Einstein introduced his theory of general relativity, he quickly realized that it had consequences he didn't quite like. A universe uniformly filled with matter would be unstable and prone to gravitational collapse. To counteract this, Einstein introduced a cosmological constant that represented a repulsive force counteracting collapse. Others understood that not accounting for this constant could lead to a non-static universe. In such a universe, the fabric of space would either expand or contract over time. Einstein's correction didn't work, and the cosmological constant led to an unstable universe. Regions with higher density would collapse, while those with lower density would expand. In a universe governed by the laws of general relativity, filled homogeneously and isotropically with matter and radiation, staticity couldn't persist. It had to expand or contract depending on the content and quantity of the universe. And so, distant galaxies are receding from us faster the farther they are. The reason lies in the fact that a universe that adheres to the principles of relativity, isotropy, and homogeneity, while filled with matter and radiation, cannot be static. It must either expand or contract based on its content and quantity. This situation could have evolved due to various factors. Redshift fatigue. Light coming from distant galaxies loses energy as it travels through space, potentially resulting in a decrease in observed energy and a perceived redshift. High-speed motion. Rapid movement could cause the fastest galaxies to become the most distant over time. Initial explosion. An initial explosive event could push galaxies further away from us. Expansion of spacetime, the last possibility, but the one supported by a comprehensive set of data, including general relativity and the physical distribution and properties of observed galaxies. By the 1930s, it became clear that there were only two options, and the universe is indeed expanding. This was further confirmed by the fact that the redshift of objects correlated well with calculated distance and observed expansion velocity, regardless of the object's distance. But a study from 2011, represented by the red data points, provides the most compelling evidence to date that the temperature of relic radiation was higher in the past. The spectral and temperature properties of distant light confirm the fact that we live in an expanding space. Collectively, all this evidence teaches us that the universe is expanding, and most likely, this is the cause of the redshift. It's not due to motion, tired light, or the result of some explosion. Space itself is expanding. This portion of the universe we can see and study is growing over time. Since the presumed Big Bang, 13.8 billion and 8 billion years have passed, and the majority of objects whose light has reached us are now about 46 billion light-years away. As of now, the observable universe spans about 46 billion light-years in all directions from our vantage point. Beyond these boundaries, there is undoubtedly much more space, likely even infinite. Personally, I'm confident that there is more universe beyond. It's just that light hasn't had enough time to reach us. In this context, whether the universe is finite or infinite doesn't matter. It can still expand. Expanding the universe is like multiplying its size by growth factors. If it was initially finite, it will remain finite but larger in size. If it was infinite, it will stay infinite. The key point is that the universe changes, expands, and stretches. All these effects are consistent and indisputable. What lies beyond the observable universe is a topic for future videos. However, when we talk about distances in the universe, we sometimes find ourselves in a state of shock because our minds can't fathom just how immense those distances are. For example, consider a distance of 10 million light-years. But what if I tell you that the diameter of the universe is about 93 billion light-years from our perspective? The observable universe can roughly be imagined as a sphere with an observer at the center. If you were to observe in any direction, the farthest point you could see would be around 46 billion light-years away. In terms of diameter, this figure adds up to 93 billion light-years. However, if we delve into the age of the universe, this number would be much less than 93 billion. So let's try to understand today how this came to be. To answer this question, let's consider when we say that an object is at a distance of 13 billion light-years from Earth. What do we mean? Is it the current distance to the object, that is, how far it is now when the light from the object started traveling toward us? Or is it the distance that light has traveled? Due to the universe's expansion, these variations should differ significantly. But first, let's use a simple analogy for better visualization. Imagine two adjacent flights of stairs. You stand on one, and your friend stands lower on the other. Your friend tosses a ball to you with a certain speed. It takes some time for the ball to travel to you. If you know the ball's speed and the time it takes, you can calculate the distance to your friend. Suppose the ball travels at 10 meters per second, and you are 10 meters away from your friend. Now, let's complicate the scenario. Imagine both of you are on escalators, moving in opposite directions. Your escalator goes up, while your friend's goes down. Each escalator moves at a speed of 2.5 meters per second. Now, things become less straightforward. If your friend throws the ball at 10 meters per second and you start 10 meters away from them, by the time the ball reaches you, you won't be 10 meters apart anymore. It would take 1 whole second for the ball to reach you, during which you'd move 17 meters away. If you were initially 10 meters apart when the ball was thrown, the moment the ball reaches you means you started at 6 meters away. It took me 0.8 seconds for this scenario. If it took exactly 1 second, it means you started at 8 meters. Now consider that I've rounded the values for simplicity. When two objects are stationary, all three values are the same. For moving objects, they're different. As you know, the universe is expanding, so things get more complicated. When we observe the distant edges of the universe, we're looking into the past. We see light from a time when objects were closer together, and the universe expanded faster in ancient times. Unlike the escalator analogy, the rate of the universe's expansion changes over time. Today, according to modern estimates, the age of our universe is around 13.8 billion years, give or take a few tens of millions of years. What does this mean for distant objects? Let's consider the current record holder, one of the farthest galaxies known to us. When we say it's located at a distance of 13.45 billion light-years, we mean the distance traveled by the light from the galaxy, whether or not it has arrived yet. For me, at least, this seems to be the most reasonable way to measure distances in an expanding universe. In the past, distances between objects were smaller. As light travels from the emitting object to our eyes, the universe continues to expand. But what does this mean for our record holder, this galaxy? Firstly, this galaxy was at a distance of 1.1 billion light-years from us when it emitted the light that has reached us today. Secondly, the light that reaches us today was emitted and sent when the universe was only 380 million years old. Thirdly, the light traveled for 13.4 billion years, and, by definition, covered that exact distance. And fourthly, now this galaxy is located at a distance of 30.3 billion light-years from us. In reality, when you read the news, watch videos, or listen to various scientists, you may not fully grasp the distances they are discussing. So, I've listed all the possible variations. However, usually the last two options are used, either the distance traveled by light or the current distance. Moreover, if the distance in light-years is less than the age of the universe, it refers to the time light traveled. If it's greater, it indicates the current actual distance. The point is, for nearby objects and objects connected by gravity, the difference between these variations is significantly smaller. Nonetheless, I would still prefer people to be more careful with their wording and to use more precise values. If each person specifies whether they mean the distance at the time of light emission, the light's journey, or the current distance to an object, confusion would be greatly reduced. This is how distances work in an expanding universe, and that colossal number, 93 billion light-years, was achieved as follows. The reason is that the accompanying distance to the farthest observable object, namely the surface of the last scattering relic radiation, is about 14 billion parsecs, or 14 megaparsecs. This corresponds to 46 billion light-years in all directions. Thus, the observable universe can be visualized as a sphere with a diameter of about 93 billion light-years, centered on the solar system, the observer's location. Since the presumed Big Bang, 13.8 billion years have passed, at least according to contemporary science. However, this time has passed for us. But since time is relative, what does it mean for observers in other parts of the universe? Does absolute time exist for the entire universe? When we say the universe is 13.8 billion years old, does this only apply to Earth, or does it hold true for the entire cosmos? So, today, let's attempt to understand this. Who knows? Perhaps someone from a neighboring galaxy is looking at us through a telescope right now, observing the dinosaurs on Earth. Furthermore, we will discuss a very unique galaxy that, so to speak, lies beyond our universe. Our Earth exists within the Milky Way, and the ages of everything we see in it match that 13.8 billion years, or almost 13.8. This age of planets, stars, and other sources of light visible in the night sky doesn't align with our own, because as you know, the speed of light is constant. For instance, if you look at a star located 200 light-years away, you're seeing it as it appeared 200 years ago. There's nothing paradoxical about this. It's negligible when compared to the 13.8 billion years. Even if we consider a star on the opposite end of a galaxy, at a distance of 100,000 light-years, the difference is practically negligible. You might wonder if there's a significant distinction between an age of 13.8 billion years and 13.8 billion 800 million years, or even the specific value of 13,790,900,000 years. I believe the difference is inconsequential. However, if we consider other galaxies that are very distant from us, a completely different story emerges. Each point in this illustration represents a separate galaxy located at approximately 1 billion light-years from Earth. Galaxies within this structure have ages of 12 billion and 8 billion years, while the most remote galaxies are even younger. As we look farther and farther, we find galaxies that existed when the universe was less than 1 billion years old, with its age being only a small percentage of what it is today. With powerful telescopes, you could potentially see individual stars with very low heavy element content. At that time, over 99% of atoms were composed of just hydrogen and helium. Carbon, oxygen, silicon, phosphorus, iron, and other elements necessary for constructing the universe were scarce. This would result in a lack of rocky planets, organic molecules, and the chance for life. When we observe galaxies in their original state, we are essentially peering into the past. Yet, there's a crucial point to note. We aren't seeing galaxies as they are today. Rather, we are observing them from our perspective, looking into the past. For someone on a distant star or in a galaxy tens of light-years away, they would see our past. If they were 100 light-years away, Earth wouldn't have signs of nuclear bombs. We wouldn't have invented computers, ventured into space, or developed television broadcasts. For someone in a galaxy a billion light-years away, our sun would appear younger and dimmer. Earth would only have single-celled organisms. What's even more astounding is that for observers in the most distant visible galaxies, not only would our Earth and Sun not exist, but our entire galaxy wouldn't either. We'd be a collection of large gas clouds slowly coming together into spiral arms, which would eventually give birth to our home. The oldest globular clusters, currently found in the halo of our galaxy, would also be absent. Nor would there be abundant hot young blue stars, which have vanished a billion years ago. Any of these observers on another star, in another galaxy, or even at the farthest reaches of the universe, would see a universe remarkably similar to ours, an age of 13.8 billion years. A universe where observations peer into the past in all directions, where relic radiation cooled to this temperature, and where the great cosmic web would be indistinguishable from what we see. In this universe, looking at us, they'd see us in the past, just as we see them. But doesn't all of this imply that there's some form of absolute time? Initially, it might seem so, but in reality, it's not the case. If the Big Bang truly occurred, it happened everywhere simultaneously, 13.8 billion years ago. This would be true from the perspective of any galaxy. However, what if there were galaxies moving at speeds not just hundreds or thousands of kilometers per second relative to the coordinate system of relic radiation, but hundreds of thousands of kilometers per second? This speed is very close to the speed of light. Just as time goes differently for anyone moving close to the speed of light on Earth, it doesn't matter if it's a particle, a train, or a person. Though it might seem fantastical, if a planet, star, or galaxy had been moving at speeds near the speed of light for a long time, it would appear significantly younger than the rest of the universe. Imagine that when the universe was only a billion years old, a galaxy accelerated due to a series of gravitational interactions, reaching 99% of the speed of light. Over the 12 and 8 billion years since then, this galaxy would have experienced only 18 billion years. Compared to known galaxies, it would be smaller and less spread out. Therefore, the universe must appear the same to all observers everywhere. The same amount of time should pass, and the universe should possess the same large-scale properties nearly everywhere. However, for some select observers who have spent significant time at speeds near the speed of light relative to the coordinate system of relic radiation, the universe would seem very strange. The moment they slowed down, relic radiation would appear young and the universe old. The fact that 13.8 billion years have passed since the Big Bang would apply to all and everything in the observable universe. You were moving at a speed close to the speed of light. It might be difficult to believe this. However, the conclusions I've shared are based on my perspective living on Earth, in the solar system, and within the Milky Way galaxy. All these conclusions about the age of the universe and various distances are drawn from what I see. To reach these conclusions about the age of the universe, I've studied space on the plate, then what's around me. These studies are based on my perspective. Unfortunately, not everyone is as lucky as me. Not everyone can comprehend that they're part of the universe. Now, let me explain why. For example, in this image, there's a galaxy. The name won't tell you much. You might think it's surrounded by other galaxies, but that's only from a certain perspective. If you were flying through the universe and passed near it, you'd encounter no galaxies there. As far as we know from astronomical observations, this galaxy is in complete isolation. For hundreds of millions of light years in all directions, there's nothing. The bright stars, highlighted by the fractional rays in this image, are actually in our galaxy. This ultra-distant galaxy is much larger and brighter than our Milky Way. It contains 10 times more stars. Behind it lies an even more distant background of galaxies. This background accompanies similar images taken in all directions of the Earth's sky. This galaxy is located in the Pisces constellation. The density of matter in the space surrounding it is about 1 atom per cubic meter. Unlike most galaxies, which are situated along galactic filaments, it's in cosmic voids, empty spaces between them. This galaxy is so isolated that if our Milky Way were in its place, we wouldn't have known about the existence of other galaxies until the 1960s, when powerful telescopes emerged. Now imagine where we'd be if we were at Shocky or the Hooke. The Hooke telescope, used by Edwin Hubble for his research, became operational in 1917. In the 1920s, 30s, 40s, and 50s, we wouldn't have found anything near this galaxy if we lived there. Our searches would have been halted. In that case, we might conclude that our galaxy is the only one in the universe. And indeed, it's amazing that in dark nights, the universe opens up to us. This makes you marvel at how unusual our galaxy's position in the universe is. It also highlights the incorrect assumptions we can make. Having only one point of view can make it hard to understand our true place in this universe. Similarly, a point of view about the birth of the universe can lead us astray, preventing us from truly understanding how everything came into being. Therefore, it's important to consider the universe from different perspectives. In reality, this will be a continuation of this video, and we'll talk about whether it's possible to deceive space and time, and whether it's possible, purely through scientific means, to find oneself between the past and the future, or even in the same moment of time. This illustration represents our cosmic history from the Big Bang to the present day, within the context of an expanding universe. The Big Bang was preceded by a state of cosmic inflation. However, the idea that there had to be a singularity before that is dreadfully outdated. Almost everyone has heard of the Big Bang, but if you were to ask different people, from laymen to cosmologists, to complete the sentence, "In the beginning, there was," you'd receive a multitude of different answers. One of the most common responses is a singularity, which refers to the moment when all the matter and energy of the universe were concentrated into a single point. The temperature, density, and energy would have been infinitely large. This idea could imply the infection of space and time. However, this picture is not just untrue, it's likely been outdated for about 40 years. We are quite confident that there was no singularity associated with the hot Big Bang. Space and time might not have had a moment of origin at all. Let's not rush to make hasty conclusions. Instead, let's explore what we already know on this matter and, most importantly, where this knowledge comes from. Astronomical observations conducted with various telescopes allow us to examine some of the most distant galaxies we have ever seen. many of which are at unreachable distances for us. As we look farther and farther, we discover that the most distant galaxies are moving away from us at an ever-increasing speed, thanks to the expansion of the universe. Today's universe is filled with galaxies in all directions and at various distances. On average, the farther a galaxy is from us, the faster it moves away. This is not due to the galaxies actually moving within their local cosmos. The expansion of space itself is responsible for this phenomenon. This prediction was one of the unusual results derived from the theory of general relativity by Soviet physicist Alexander Friedmann. Edwin Hubble's observations confirmed it. This means that over time, matter in the universe becomes more spread out and less dense as the volume of the universe increases. This also implies that in the past, the universe was denser, hotter, and more uniform. Extrapolating backward in time, we arrive at early, hotter, denser states. But does all of this lead to singularities where the laws of physics break down? When you extrapolate the universe's development backward in time, you start to notice several important changes. In particular, you'll reach an era where gravity didn't have enough time to form sufficiently large clumps of matter for stars and galaxies to form. Then, you'll arrive at a point where the universe was so hot that it couldn't even form neutral atoms. Beyond that, there will be a state where atomic nuclei themselves break apart. Then, you'll witness the spontaneous appearance of pairs of matter and antimatter particles, and then you'll see where individual protons and neutrons will decay into quarks and gluons. The thing is, regular physics, including the moment of the universe's beginning, breaks down in a singularity. However, achieving an infinitely hot and dense state has its consequences, many of which, unfortunately, are not confirmed by observations. Each step represents a universe that's progressively younger, smaller, denser, and hotter. Continuing this extrapolation, we see that the densities and temperatures increase to infinite values at the moment when all the matter and energy of the universe were contained in a single point, a singularity. However, the hot Big Bang, as initially thought, wasn't just a hot, dense, and expanding state. The moment when all the laws of physics ceased to work was the birth of space and time. It's a way to suddenly make the entire universe appear out of nothing. It was the original act of creation. The singularity is associated with the Big Bang, but if everything happened as described, and the universe in the past had infinitely high temperatures, there would be certain obvious signs observable even today. However, for now, let me remind you what fluctuations are. Fluctuations are oscillations, meaning any random deviation from a certain value. In the context of the Big Bang, there would be temperature fluctuations of enormous amplitudes, temperature fluctuations that would be limited by the speed of light. They would only occur on scales not larger than the cosmic horizon. Relics of high-energy cosmic materials, such as magnetic monopoles, should have remained, but temperature fluctuations don't exceed 1 part in 1,000, which is 1,000 times smaller than what the singularity-based Big Bang predicts. Fluctuations larger than the horizon have been confirmed by various satellites, but the constraints on the existence of magnetic monopoles and other relics of ultra-high energy are extremely strong. The absence of their presence has serious consequences. The universe never reached extremely high temperatures, so there must be some boundary. We can't extrapolate back infinitely far to a hot, dense state with infinitely high temperature. Moreover, there's a limitation on how far we can go while accurately describing our universe. In the early 1980s, a theory emerged that before our universe was a hot, dense, expanding, cooling, matter and radiation-filled state, it underwent a phase of inflation. The presence of a cosmic inflation phase should have meant that the universe was filled with energy inherent to space, leading to rapid expansion that stretched the universe into a flat state with uniform properties everywhere. This would have involved small amplitude quantum fluctuations at all scales. Inflation causes space to expand exponentially, which can rapidly cause initially curved or uneven space to appear flat. And even if the universe were curved, its curvature radius would be at least hundreds of times larger than what we could detect. When inflation ends, it converts the energy inherent in space itself into matter and radiation, giving rise to the hot Big Bang. However, this doesn't lead to an infinitely hot Big Bang. only one that reaches a maximum temperature hundreds of times lower than what's needed for a singularity. In other words, it leads to a hot Big Bang emerging from an inflationary state, not a singularity. The information existing in our observable part of the universe that we can measure only corresponds to the last few seconds of inflation and everything that happened after that. If you were to ask how long inflation lasted, you wouldn't naturally find an answer to that. It continued for at least a little longer than those seconds, but whether it continued a bit longer than that, significantly longer, or for an infinite amount of time, that is not just unknown, it's fundamentally impossible to know. But then, what did inflation give rise to? Many studies and discussions revolve around this topic, yet no one knows the answer because there's no evidence to rely on. There were no observations that could have been straightforwardly made. Consequently, some individuals or scientists make mistaken claims. For instance, one of the claims was that we had a theory of singularity-based Big Bang, which generated a hot, dense, expanding universe before we learned about inflation. Inflation is actually an intermediate stage, so we get the following sequence: singularity, inflation, hot Big Bang. There are numerous graphs and images created by leading cosmologists that illustrate these data, but it doesn't mean they are all accurate. They illustrate density fluctuations and gravitational waves arising after inflation. The assumption of a singularity before inflation doesn't necessarily hold. There's a very strong basis to believe that it's not the case. Mathematically, we can demonstrate the impossibility of transitioning from a singularity to an inflationary state. And that's why the space-time of inflation expands exponentially. Imagine how an exponential function works. After a certain amount of time passes, the universe doubles in size. After twice that time, it doubles again, which means it becomes 4 times larger. Wait for 3 such intervals of time, and it triples. Wait for 10 or 100 such time segments, and these doublings will make the universe 2 to the power of 10 or 2 to the power of 100 times larger. This means that if we go back in time for the same duration, or for 2, 3, 10, or 100 times longer, the universe will become smaller and smaller, but it will never reach zero. It will always be a fraction of its initial size, such as half, a quarter, an eighth, 2 to the power of minus 1/10, or 2 to the power of minus 100. No matter how far back in time we go, we'll never arrive at a singularity. The blue and red lines represent the traditional scenario of the Big Bang, where everything begins at time t equals 0, including space-time. In the inflationary scenario, represented by the yellow color, we never reach a singularity where space takes on a singular state. It could become arbitrarily small in the past, while time continues infinitely. Among cosmologists, it's well known that there's a theorem demonstrating the incompleteness of the past inflationary state. This means that all particles existing in the universe, undergoing inflation, will eventually meet when extrapolated backward in time. However, this doesn't imply that the singularity necessarily existed. Inflation simply doesn't describe everything that happened in the history of the universe, including its birth. It is also known that inflation cannot arise from a singular state, as the region undergoing inflation must always start with a finite size of space-time fluctuations on a quantum scale during inflation, which stretch across the entire universe and give rise to imperfections in density and gravitational waves. However, whether inflation emerged from a singularity or not is unknown. So every time you see a diagram, article, or history about the singularity of the Big Bang that existed before inflation, know that you are dealing with outdated scientific facts. The idea of the singularity of the Big Bang lost its relevance as soon as we understood that there was another state before the hot and dense state of the Big Bang, cosmic inflation, which likely prepared and initiated the Big Bang itself at the very beginning of space and time. Possibly, a singularity from which inflation emerged existed, but there is no guarantee. In science, there are things that can be checked, measured, predicted, confirmed, or refuted. For instance, inflation giving rise to the hot Big Bang is substantiated. Everything else is merely idle speculation. Therefore, to understand how our universe was born, it's worth considering all possible scenarios of events. If you ask any scientist if the universe has a boundary, you will likely receive an ambiguous answer, Because on one hand, the universe has an end from our perspective, particularly in terms of observations. This is known as the observable universe. But if we look at science from a different angle, we understand that our universe is expanding with acceleration, thus there cannot be any limitations. You will get approximately this answer, but only with detailed arguments, formulas, and explanations of why everything is the way it is in this world. It's known that due to the expansion of the universe, there exists an event horizon beyond which we cannot penetrate. We are witnesses to the fact that there is at least one intelligent life form. Believing whether we are alone or if there is someone else out there is a personal matter for each individual. However, let's imagine that in a distant galaxy there is another civilization, and naturally the event horizon for them is of the same size. And from their point of view, they could observe those parts of the universe that are beyond our horizon. Roughly speaking, they know what is unknown to us. Let's assume that an interesting cosmic phenomenon or a unique galaxy they observed astounded them so much that they wanted to tell us about it. With the help of some mega-advanced and unique future technologies, we receive their signal with this information. In that case, we would learn what lies beyond our event horizon. What do you think? Is this theoretically possible without violating the modern and known laws of physics up to 2019? So let's delve into all this in more detail. On one hand, we can trace the universe's history back to its very beginning, to the Big Bang 12 and 8 billion years ago. We have this magnificent image of the universe captured using background radiation. We can also observe stars and galaxies that formed during that time within the reach of modern telescopes. At the moment, the record is held by light that traveled to us for 13.7 billion years from an object currently 33 billion light-years away. Only the most advanced telescope could surpass this record. But the essence is that our observations are limited to the observable part of the universe since the moment of the Big Bang. Light traveled 13.8 billion years, meaning we can only see the light that traveled that many years in any direction. However, this doesn't mean there's no universe beyond this border. We're sure it's there. After all, light still reaches us, and the question is about how much of it is there. And here, our experiment begins. If there's a limitation on what can be seen, then this limitation also applies to those observers whose light is visible differently. In other words, if we take two galaxies situated on opposite sides of us, and the light from them traveled 13.7 billion years, we can see both of them, but they won't see each other. If each of them has intelligent beings, couldn't they send us information about what they see, which is unavailable to us? Could they thus deceive the limitations of space-time and provide us with information about the part of the universe we can't see? Or could we send them images of the faraway galaxies captured by the Hubble extreme, or even a map of the universe as we see it? If we continue exchanging this information, would each participant eventually know more than they can see with their own eyes? However, there's a catch. Let's remember light from a very distant object. The thing is, that light would be old. If we see something whose light traveled to us for 12.4 billion years, and the object is now 33 billion light-years away, we see it as it was 400 million years after its creation. Of course, it's a distant galaxy and is still emitting light, but we'll never receive it. The universe isn't just expanding, the expansion is accelerating, and this is a firmly observed fact. The question is why it's accelerating. The biggest explanation for this is dark energy. We'll talk about that later, at least explaining what's generally understood as dark energy. So the light emitted by galaxies beyond certain limits will never reach us. If it weren't for dark energy, we would eventually see it and receive the information they sent, but only after the light emitted by those galaxies reached us. Therefore, we can get information from objects beyond our horizon, but only after they move inside our horizon. And due to dark energy, whatever gets inside our horizon is already gone. This viewpoint is examined from one perspective, taking into account the theory of the Big Bang as the beginning of the universe, and nothing prevents us from discussing it in a few episodes.